All right. Can you hear me? Okay. I'd like to thank FinTech DevCon for having me here, the conference organizers and sponsors, especially Moov. I'm really honored to be speaking here today. I'll be speaking today about event-based architecture for payment platforms. My name is Erika Newland. I'm a senior software engineer and technical lead at Orem, where I've led teams building ACH payments, account-to-account payments, and most recently I'm leading a team building our seamless customer integrations and onboarding experience. Prior to Orem, I worked at N26, where I worked on consumer-facing payments. Orem solves the most complex problems in money movement. We unlock 24/7, 365-day-a-year payments, and we orchestrate complex multi-rail, multi-directional payments in a single unified platform, and we do B2B2B and B2B2C. Orem is using an event-based architecture to solve the complexities of payment problems. These include cannot fail resiliency, complex orchestration, and time as a processing parameter. Our event architecture stack leverages lightweight AWS-managed services deployed in reusable infrastructure as code modules that fit together like Lego building blocks. We think about our event production system from the perspective of our event producers and our event consumers separately and attempt to solve problems individually at those two ends of the spectrum. One of the biggest risks in payment platforms is the risk of losing a payment halfway through processing. And this can happen in a failure to communicate either synchronously or asynchronously between your microservices. Orem leverages a transactional outbox model to solve for this problem. In our transactional outbox model, we write transactionally to both a domain data table and to the outbox table, and we leverage RDS's transaction blocks to ensure a rollback if we fail to write to one table. We then use what we call our Outbox Polar module. This is an infrastructure as code module that packages an AWS node Lambda driven by a cron and a Kinesis data stream. The Lambda is responsible for reading from the table event rows that are eligible for event publication, publishing them to the Kinesis data stream, and updating the table to indicate that the events have been successfully published. If the Lambda fails to write to the Kinesis stream, it simply does not update the table, and the rows are picked up for processing the next time the Lambda runs. Another important risk or challenge in payment platforms is ensuring that you're delivering data both to long-term storage and data analytics, as well as your microservice consumers. We use what we call an event producer module to solve this problem. The Kinesis data stream, written to by the Outbox Polar, triggers an AWS Lambda, and that AWS Lambda simultaneously fans out to both a Kinesis data firehose to serve our analytics and long-term data storage layer, and to SNS topics that are subscribed to by our consumers. What's unique about both the event producer module and the Outbox Polar module is that we're packaging not only our AWS services with those modules, but we actually package the JavaScript code that runs the Lambdas. And in this way, we're able to deploy identical code from a centralized location across our ecosystem. While we use standardized event producer modules for event production, event consumption requires domain-specific solutions customized to the consumer. And we address problems including complex orchestration and time-based processing with these customized solutions. So in payment platforms, it's pretty common to have a step in the lifecycle of the payment that requires more than one input for processing to progress. And we use what we call event coordinators to address this challenge. Our event coordinators are really just specialized event handlers that are tasked with unwrapping an incoming event, storing that event in a domain-specific schema to the consumer, checking to see if the subsequently required events have arrived, and then releasing a new event to promote the life cycle of the payment if both events have arrived, otherwise returning success to clear the message off the SQS queue. So to get a sense for how this works in practice, I'm going to walk you through an example. This is an example with our settlement creation coordinator. For some context, the settlement creation coordinator requires 2 events to create the settlement workflow. It requires what we call a decision event, and that decision event tells the system how long to wait before completing the settlement lifecycle. And it requires a transfer completed event that tells the service that the transfer has been submitted or the payment has been submitted to the payment network. And the settlement workflow, when it completes, is what ultimately makes funds available to our enterprises, and so is a really important aspect of our payment platform. So in this case, we have an Amazon SQS queue, which is consuming messages off of the SNS topic. If the decision event comes in first, the settlement creation coordinator unwraps that decision event and stores the decision in a domain-specific decision table. So any information in the event that is not pertinent to the consumer is dropped at this time, and only the valuable information is stored. The coordinator then checks the transfer table to determine the status of the transfer, and this is a proxy for whether the transfer completed event has arrived at the microservice. And if both events have arrived, so we have the decision event and evidence of the transfer completed event, then we write a settlement workflow creation event to the outbox to create that settlement workflow. If it hasn't, we return success, so the message is cleared off the SQS queue. So when a transfer completed event comes in, the transfer's own workflow will have updated the transfer status at the transfer table, so there's no work to do there. The settlement creation coordinator checks the decision table to determine if the decision has arrived, and again, writes a new event creating the settlement workflow to the outbox or return success. So another challenge with payment processing is that payment life cycles often require time as a processing component. And we use what we call cron-based event gating to handle this scenario. So in cron-based event handling, we have a processor. That processor could be an event coordinator or a singleton event handler. It handles a payment message, and that processor is tasked with calculating the release time for the payment lifecycle. We then write the release time to a specialized hold time table and to the outbox to indicate that the payment is in a held state. And we use a cron-driven lambda to read from the hold time table to find the rows for which release time has passed and to publish a release event to the outbox and subsequently to the event producer. So 2 things to note here. This lambda never updates the state of a payment. We always allow the payment workflows to update the states of the payment. We simply release an event that triggers the workflow to do that. The other thing to note here is that we have found that using a separate hold time table is really valuable for cleanly and clearly separating concerns between the domain tables and this event-based, this cron-based event gating system. So, in conclusion, Orem uses an event-based architecture to solve the hardest problems in payments. We use reusable event producer modules deployed as infrastructure as code, and we leverage lightweight AWS managed services to deploy these infrastructure modules. Domain-specific consumers come together to solve resilience, orchestration, and time-based processing problems with payments. And you can learn more about what we're doing at orem.io. Thank you. So we have time for questions. I'd love to take any. Yeah. So the question was, are the coordinators using a standardized third-party orchestration framework? We are not. We wrote these kind of in our service code in kind of separate directories. The logic is actually fairly simple, and the goal for the coordinators is to be kind of as simple and as easy to read for our engineers making changes as possible. So we found that we didn't actually need an additional orchestration layer for these. Yep. The question was whether we'd consider step functions for coordinators. So I do think step functions have an interesting role to play. In this case, because it was really only 2 steps for most of them, the overhead of leveraging those in addition to, so these are in Go microservices, so the coordination between those is challenging in a way that we could really simply deploy these coordinators in a system that was already running. That's a good question.
When you have the coordinators, is there a chance you end up in a deadlock? And how do you handle those?
The question is there a chance that you'll end up in a deadlock with the coordinators? And you mean as we go to write to or read from the table?
Yeah, you have 2 events that are waiting for each other to happen at the same time.
Right, right. Yeah, so the best way that we've found so far, we have not run into deadlocks. Locking the tables at the right point at read so that the other process is waiting is what we're hoping will work. We have not found deadlocking problems. And part of this is that we also know that there's a likelihood that these won't be coming at the exact same time. And that helps as well. So they're usually separated. So the question was, how do we roll back the payment? And so are you talking about at the coordinator step? So what we found is that because we use a separate process to always update the state of the payment, and the coordinators are only producing events that the workflows use to trigger the next step, we don't actually have a scenario where we need to roll back the payment because we don't promote the payment until both events have come in. So we store one event that we need, we check for the other event. If it's not there, we do nothing. It's a no-op. If it's there, we produce the event that promotes it. So we never actually have to roll back. Yeah?